So now we're going to look at curvature in rectangular coordinates.
And?
Well, see, if C is a graph of a twice differentiable function given by y equals f of x, so now we're in rectangular coordinates here. Then the curvature at xy, see, we never talked about curvature before when we talked about simple functions that weren't vector valued functions, but we now have a way of doing that. We've got other ways to construct curvature, but we can mostly write our vector valued function r of t as x of I plus f of xj plus 0k, and then we are in fact looking at a function that looks like y equals f of x, or the graph would be the same as y equals f of x. It would be in the xy plane, and so the curvature of that graph follows our other curvature formulas. So if you go back to 12.8, you can probably see why this is so. Remember, this has a square root in it, so anyway, let C be a curve with curvature kappa at point P. The circle passing through P with radius 1 over kappa is called the circle of curvature. If the circle lies on the concave side of the curve and shares a common tangent line with the curve at P, the radius of the circle is called the radius of curvature, and the center of the circle is called the center of curvature. Sometimes I've seen this circle of curvature called the osculating circle. That means the circle that most closely resembles the curve at one point. So here's a question: at what point on a parabola would the radius of curvature be the smallest? And sort of have an answer for that typed in there, and that would be at the vertex. Think about the graph of a parabola, right? Then a circle of curvature here would have a very large radius, and a circle at the vertex would have a much smaller one. So for the parabola y equals 4 minus x squared, find the circle of curvature at the point 0, 4, and also at the point 2, 0, 2 different points on that parabola. So, well, we've got our formula here. So, for this parabola, find the circle of curvature at the point, well, we need our curvature. So, y double prime over 1 plus y prime squared to the 3/2. So we need y prime, which is negative 2x. That's the derivative of this term, plus 0. And then y double prime is negative 2, and the absolute value of that, of course, is just 2 in the numerator. Then we have 1 plus y prime squared, so that's 1 plus 2x, negative 2x, quantity squared, to the 3/2. So therefore, this simplifies a little bit to 2 divided by 1 plus 4x squared to the 3/2. It might be worth me writing that. So I will go ahead and write that here. That is 2 divided by 1 plus 4x squared to the power 3/2. Okay. Now, at the point 0, 4, that's x is 0, y is 4, which would be the vertex of this parabola. We have x is 0, so that's 0. We have 2 over 1, so the curvature kappa equals 2. And the radius of curvature would be 1 divided by 2, which is 1/2. The center would be at the point 0, 3.5. Do you see why that is? Since the radius is 1/2, it's just a little bit below the vertex. And so the circle is x squared plus y minus 3.5 squared equals 1/2 squared. That would be the circle that is closest to our parabola at that point. So if you will, I took the liberty, since we've got our osculating circles equation here and we have the graph of the parabola, I took the liberty to draw that parabola, 4 minus x squared, and the circle of radius 1/2, whose center is at 3.5. And what I did, I just took this equation, and I admit I did it the quick way. I used my software, but I solved it for y. Of course, you could subtract x squared from both sides and then take the square root of both sides, and you would get this. It's a plus or minus, because when you do square root, you'd have to do that, and then add 3.5, add 7/2 in other words. So I thought maybe you'd want to see that as an interesting picture, because there is that circle of curvature at the point 0,4. And you can see quite clearly how well the circle and the parabola match up. Okay, at the point 2, 0, the curvature is x is 2, y is 0, so we'd have to put a 2 in here for x, so that would be 17 to the 3/2, so it's 2 over 17 to the 3/2, 2 over 17 squared to 17. Okay, that would be the curvature, kappa equals this number, and the radius of curvature would be 17 squared to 17 over 2. The tangent line is y equals -4 times x minus 2, and the perpendicular to this passes through the center of the circle, so the center is on this line, and is 17 squared to 17 over 2 units from 2.0. Call the center hk, and we have h minus 2 squared plus k squared equals 17 squared to 7. So the point is also on the line y equals 1/4 times x minus 2, and we also have k equals 1/4 h minus 2. Substituting for k in the distance formula, we get, substituting this in for k in the distance formula, we get h minus 2 squared plus 1/4 of h minus 2 squared equals, this is this number squared. That's I guess it would be 17 cubed or something like that over 4. And solving this, I admit I used my software to solve it, and I got -32 and 36. So we would have to ignore the positive answer if you think about where the position of this circle would be on this parabola at the point 2, 0. When x is 2, y is 0, the circle would have a center down in this region somewhere. So we would ignore our positive answer and just go with a negative. H equals -32. So we get h equals -32 and k equals -17/2. So our circle would be x minus -32 squared, y minus -17/2 squared equals 4,913/4, and there it is simplified. So I'm not going to draw that one, but I could. I think I'd really have to expand my axes up there a little bit, but I did draw one of them, so you got the idea.